Now let's ask one question that what is the typical size of adders we would require in regular computation? So when we started doing computation, when we started building computer, then usually we used to work on 8-bit computers. So that means usual data type used to be 8-bit. And then we started working on 16-bit, then 32-bit, then 64-bit. These days in our computers, most of the computations are 64-bit computations, which essentially means that the delay of this particular adder would grow linearly as we grow the size of my addition, which could be hugely impacting things, because this addition is a very fundamental unit in any digital design. You would require addition invariably in most of the circuits. So if the delay will keep on increasing as the size will increase, it's going to be a very costly operation. So it's very important that we reduce the delay of this addition. How can we reduce the delay of addition? To reduce the delay, let's understand from where the delay is coming. So we have seen in our previous slide and previous information, we see that the delay is actually because of this carry, and sequential generation of carry and sequential consumption of carry. Both of these things are important. So unless my carry is generated, it cannot be consumed, and carry at ith stage cannot be generated unless carry of I-1 stage is there. So unless we break this sequentiality, unless we are able to generate this carry in a faster way, we cannot have a fast adder. So we have to, if we want to reduce the delay of a adder, we have to generate this carry parallelly. To how to generate this carry parallelly? So let's look at how carry is actually generated. So in a single bit, we see that carry is generated when both, we are talking about ith stage, any particular stage. Let's say ith stage, carry would be generated when both ai and bi is 1. ai and bi are 1. Let's talk only about the primary input. So these primary inputs, if both of them are 1, then carry would be definitely generated. But sometime carry need not to be generated in ith stage to be there in the ith stage, to be there in the I+1 stage. So sometime a carry is coming from behind, or some of the stages, I-2, I-3, I-4, some of the previous stages, then also carry could be there as an output, like Ci+1 could still be there because carry was generated somewhere in the previous stage. So how a carry which has been generated in the previous stage will come as the output at ith stage? Because it would be propagated, and for propagation the requirement is either ai is 1 or bi is 1. So when either of them is 1 and there is a carry input from the previous stages, then it would be propagated. 1 plus 1 will become 0. So because there was a carry from the previous stages, it will also be propagated. So and the third parameter is when this propagation would be halted. We call it carry kill. So when both ai and bi is 0, then whatever carry was coming from behind, it will stop propagating. We can also say that we are killing that carry. The carry will not go to the next stage. So these three terms are very important to see how a carry is generated, how carry is propagated. So if we try to see these three piece of information and we try to analyze it further, then we can say that yes, how we would understand how we can generate this carry in a faster manner. Okay, so let's call this carry propagation signal carry generation signal as Gi, which is equal to Ai and Bi. So when both of them are 1, then generation is 1. Propagation is equal to Pi at any particular stage. Propagation is equal to Ai plus Bi. Then you will ask me that we have said here that Pi is equal to, propagation would be there when either of them is 1. So essentially Pi should be equal to Ai XOR Bi. So that means when either of Ai or Bi is 1, only one of them is 1, then propagation is true. So why we are writing this? Yeah, that's a valid question. Now see, this propagation has a slightly different definition. This propagation means this also included generation. So that means that even when both of them are 1, then also propagation would be there. Okay, so when carry, this propagation means either it would be generated or propagated. So this Pi definition is more generic, which means that carry would be propagated. So that essentially means if there is a carry from behind and if Pi is 1, then it would be propagated to the next stage. So which definition of Pi should we take? So this definition of Pi is less costly in terms of delay. So here the delay of Gi is equal to 2 input AND gate, and here the delay of generation of Pi is equal to 2 input OR gate. Both of these delays are equal as well as small, but the delay of generation of this XOR is little more than AND or OR. So that's why many a times we prefer this definition from the delay perspective. Okay, so we can now say that a carry in a particular stage would be, carry out in a particular stage would be 1 if it is generated in this particular stage or it has been propagated from previous stages. So let us see if we can generalize it for 4-bit adder. So we have taken the definition here also. If carry is at a particular, C out of a particular stage is 1, either it is generated at this particular stage or propagated from the previous stage. So I can write C4 is the last stage of my 4-bit adder. So C4 would be 1 if it is generated in third stage, generated in third stage, or it is propagated from third stage and there was a carry in from the third stage. Similarly, we can also say that carry for the third stage is equal to it is generated at the second stage and it is propagated from the second stage and there was a carry input onto the second stage. Similarly, we can also say that the carry at the second stage is equal to either it is generated at the first stage, C out at the first stage would be equal to either it is generated at the first stage or it is propagated at first stage, or there is a carry input to the first stage. Now this is actually in the terms of primary input. So carry out at the 0th stage would be equal to if either it is generated at 0th stage or it is propagated at 0th stage and there is a carry input. So this equation we can generate from the primary inputs. C0 is our primary input. P0 can also be calculated from the primary inputs A, B, C, A and B. Similarly, generate can also be calculated from primary inputs. Now this C1 we can substitute here and we can calculate the value of C2 in terms of primary input. So if I do that, it becomes generation G1 plus P1 into G0 plus P1 into P0 into C0. Now whatever is the output here, that we can keep as a we can substitute here at C2 and we can find out the value of C3. So C3 is G2 plus P2 G1 plus P2 P1 G0 plus P2 P1 P0 C0. Now we can substitute the value of C3 here and we can find out what is the value of C4. So C4 is equal to G3 plus P3 G2 plus P3 P2 G1 plus P3 P2 P1 G0 plus P3 P2 P1 P0 C0. So what does this equation mean? This equation essentially means that at nth stage my carry would be out if it is generated at nth stage, or it is generated at n-1 stage and propagated through nth stage, or it is generated at n-2 stage and propagated through n-1 and nth stage. Similarly, we have to go till carry 0. Okay, so this particular equation of C4 at carry at any particular nth stage essentially means that the carry depends on all the stages. Cannot ignore that. But we can compute it from the primary inputs. We can calculate directly from propagation and generation, which could be generated from A and P. Now there is another thing which we have to see, that this is the equation for carry 4. So if I need to find out carry at any nth stage, the size of this equation will keep on growing, as well as the number of input, maximum number of input to this equation will also keep on growing. So for example, you see the delay of this to generate C4 would be equal to what is the critical path for the AND gate, what is the maximum delay for the AND gate. Maximum delay will come because of this. So this would be 5 input AND gate, and similarly there would be a 1, 2, 3, 4, 5. There would be 5 input OR gate. So the total delay would be 5 input AND gate plus the delay of 5 input OR gate. Now to make so this particular type of adder where we are generating carry from our primary inputs P and G. P and G is calculated from primary inputs, propagation and generate, and then we are calculating the carry simultaneously. We call it carry look ahead adder. So that means we are looking ahead for the carry before actually is carry propagated. So in short, we are calling it CLA, carry look ahead adder. Now let's try to see how it would be in terms of circuit. So now when I would like to design a CLA circuit, what I would do is I will design a adder circuit in which I will modify it a little bit. In the modification, what I'll do is I'll have still 3 inputs, C0, A0, B0, or C, A, B carry in, AI and BI, but there are 3 outputs. One is sum, another 2 outputs are generate and propagate at any ith stage. So propagate would be AI or BI, generate would be AI and BI. So similarly for all these stages we'll have generate and propagate, and then there could be a carry generation block which can use all these equations to find out the carry value of C1, C2, C3 and C4, and all these carry values C1, C2, C3 and C4. So all these values of C1, C2, C3, C4 would be generated output as output of this carry generation block. Now C1 would be given to the input of adder 1, C2 would be given as an input to adder 2, C3 would be given as an input to adder 3. So this is 3 actually. So this way we would be able to design it structurally, and we can code it in model it using a Verilog also in a similar way. So let's try to analyze what would be the delay for this 4-bit CLA adder. So to simplify the delay analysis, let us say that input the delay of AND and OR gate is going to be delta G, irrespective of number of inputs. Irrespective of fan in or fan out, we are assuming that there is a delta G delay for one gate. So we are talking about AND and OR here, we are not talking about XOR. XOR one XOR delay could be, from this definition, it would be equal to 2 delta G. So the total delay would be equal to, in one gate delay, or one delta G, would be computing all the propagation and generation. So all these Pi and Gi would be available after one delta G, and after that there would be 2 delta G required. So 2 delta G would be required to generate all these carries. That means C1, C2, C3, C4, all of them would be generated in 2 delta G. So once carry C3 is generated, then I would require another delay for calculation of sum. So this sum would require an XOR gate. So XOR gate, we would again consider that 2 delta G would be required. So the total delay would be 7 delta G. You can also analyze that in case of a ripple carry error, the total delay was going to be, there would be, the delay would have been 2 delta G for all of them plus 1 XOR gate delay. So essentially there would be 4 plus 8 delta G delay. Now you see the advantage is not that sufficient. So this way we are able to reduce the delay of a 4-bit adder. Now at what cost? We have increased the area. So this whole additional circuitry of carry generation block is the additional area consumption. The circuit which was required for all the adder 0, adder 1, adder 2, adder 3, it has not reduced. It is still there. The same circuit is there. In addition, we have introduced these additional AND and OR gates to generate to get this generate and propagate signals, plus this carry generation block, which is also an additional area. So with this additional area, we are able to reduce the delay somewhat. Now let us see, this was a 4-bit CLA adder. What about if I want to design a larger adders? Let's say 16-bit adder. So ideally we should take 64-bit adder, but 64-bit adder would become slightly complex for demonstration. So let's take 16-bit adder. We can generalize it to 64-bit adders also. So the problem with 16-bit adder would be this carry generation would require now large fan-in. So for example, if I want to generate C16, to get the C16 signal, I would require AND gate with 17 inputs, OR gate with 17 input. The delay model which we have used in CLA, while talking about CLA, we said that AND and OR gate delay would be same irrespective of fan-in. But that will not be scalable here. So we can still say that using some transistor level techniques, by properly sizing the transistors, delay of 3 input AND gate and 2 input AND gate could be very similar, but 17 input AND gate delay cannot be same as 2 input or 3 input AND gate. So that assumption of same gate delay for large fan-in will not be applicable at all. So that means this method is not scalable. Similarly, area implications is also going to be huge, because to generate this 17 input AND gate or 17 input OR gate, we would require multiple level logic, and that multiple level logic would contribute to delays. Similarly, it will also contribute to area. So your area will also keep on increasing as we increase the number of these stages in our look ahead. So that essentially means that this CLA is not a very scalable approach. This gave us some idea how we can generate carry in a faster way, but if we go beyond 4-bit CLA, then it may not be scalable. We have to experiment. So some maybe 8 input CLA can also be okay, but if we go beyond, then it's not scalable at all. What should we do? the alternative are, so either we use the blocks in 4-bit CLA and then we use multiple of such blocks, or we can also use multiple level CLA. So let's see both of them one by one. So if we are using multiple blocks, then what would happen essentially, that you will have this as a group 0. In group 0 you'll have A0 to 3 as an input, B0 3 as an input, and similarly the 4 it would be a group of 4. So for 16-bit CLA I would require 4 such units. Okay, and then the carry would be now rippling from one group to another group. Okay, so does it seem better? Is it faster than our regular adder or not? Let's quickly do this analysis. So from a 4-bit CLA perspective, the advantage was not much. In case of ripple carry adder, we were seeing the delay as 8 delta delays, 8 delta G delays. Here in 4-bit CLA it was 7 delta G delays, but in case of 16-bit it could be substantial, because now generate and propagate of all of them could be generated at once. So there would be a delta G delay for generate and propagate at all these stages. While this carry propagation, carry generation, here the carry generation would require 2 delta G, and similarly after 2 delta G C4 would be available, and another 2 delta G C8 would be available, at another 2 delta G C12 would be available. So the total number of transactions here would be, like you will say, n by 4 number of 2 delta G delay would be required to generate all the carries. Okay, so we are assuming C16 also need to be generated. So after C16 is generated, yes, so the total amount of, then after once this C12 is generated, then you would also require when C16 is generated, after that you would further require 2 delta G for calculating the sum. The overall delay would become equal to n plus 2 plus 3 delta G. So if it is n is equal to 16, so that means it's a 16-bit adder. So the 16-bit adder would actually require 11 delta G delays. While in case of a ripple carry adder, for 16-bit adder it would require 32 delta G delays. So the advantage of CLA is clearly evident if we increase the number of bits. It would give us n by 4, so at least it would give us asymptotically we see the delay would be reduced by n by 4 or divide by 4. So if the delay for 64-bit adder in a regular case is x, then delay in case of a CLA we are using block of 4, then it would be x by 4. So delays would be quite less, but yes, can we do slightly better, or is there any better approach? Then we can use this carry generation and propagation in a hierarchical manner. So when we do it in a hierarchical manner, it can look something like this. So we are applying it again and again. Now this is the previous the same diagram we had drawn, but in a slightly different way. So there is a group 0 which is taking 4-bit input. Similarly another group group 1, group 2, group 3. So here we'll have 4 groups: group 0, group 1, group 2, group 3. So we are taking this example for 16-bit addition. Now all these groups will have a 4-bit addition taking place in all these groups. Now if we apply that method again, we say that the output of each of this group will generate sum, which is 4-bit input. Additionally, all of these groups, along with doing the way what they were doing internally, so that means they had their own carry generation and propagation blocks, which was based on the primary input A and B. So based on that, they also generate two additional signals, which is called group generate and group propagate. So each group or each first level CLA is doing carry look ahead computation within itself. So when it is doing it itself, so that means it is generating propagate and generate signals, and using those propagate and generate signals, it is computing the sum. So along with generating its own propagation and generation signal, it also generate group propagate and group generate signals. So each of this group is generating two additional signal, which is group propagate and group generate. So these group propagate and group generate signals can be given to another hierarchical block, which is carry generation block. So this carry generation block, the definition of this carry generation block is exactly similar to the carry generation block at the first level, which is also present in all these groups. But now this particular carry generation block is working on not only from the primary generate and propagate signal, but it depends on group generate and group propagate signals. So what this group generate and group propagate signals, I'll tell you in the next slide. So but for now, let's try to understand that each group, so whether there would be generation from this particular group or not, whether there would be propagation. So if there is a carry here, whether it would be propagated as a C4 or not. Okay, so that would be group propagate, and similarly group generate would be whether there would be carry at this particular stage or not. So whether there would be a carry at C4 or not. Okay, so this particular method can help us in generation of carry in a even hierarchical, even in a faster way. Now we can find the carry at C4 in a lesser time, so that we'll do a quick analysis now. Now this hierarchical nature of this particular CLA, where we can have a carry generation block here, which is at the second level. So there could be this group generation and group propagation can even be enhanced further. So let's say we would like to create a 64-bit adder using this 16-bit adder. So each 16-bit adder can generate another group generate and group propagate, which can further be used to generate the carry for the next set of blocks. So if we do in this way, then the total delay of any largest carry and any largest adder would not depend on linearly on size of adder, but it would depend on the log of that n. So we are creating sort of a tree. So because of this tree structure, now we are reducing the delay at each particular stage. So let us see what is this group generate and group propagate. So group generate essentially means that a carry is generated in this particular group. It's not talking about, so when we are saying group generate at this stage, it doesn't know whether a carry came from zeroth, whether carry is there from C0 or not, but within this group, whether it is generated or not, that is what is the important thing here. So to know whether a carry is generated in that particular 4 bits, so we can use this particular equation which we have seen earlier. So that means carry is generated in the 3rd bit, or carry is generated in the 2nd bit, or it is propagated at the 3rd bit. Similarly, carry is generated at the 1st bit and propagated through 2nd and 3rd bit, or carry is generated at the 0th bit and propagated through 1st, 2nd and 3rd bit. So this is the group generate logic equation for 4-bit group generate. Similarly, if there is a carry from the previous stage, whether it would be propagated out or not, that means all of them has to be propagate, so there has to be propagate in all the bits. So group propagate means that carry is propagated through P0, P1, P2, P3. So for all the 4 bits, if carry is propagated, that means group carry, for that particular group, carry would be propagated from previous carry to the next carry. So if we have this G star as a group generate and P star as the group propagate, then we can write the equation for our C4, C8, C12 and C16 accordingly. So C4 would be equal to, if it is carry is group generated by group 0 and there was a C0 input and it was propagated through through group 0. So similarly for group 1, if it is generated at group 1 or it is generated in group 0 and propagated through group 1, or there was a carry input and it is propagated through group 1 and group 2. So similarly C4 is C18, C12 is if it is generated in the second block or generated in the first block and propagated through second block, generated in the zeroth block and propagated through first block and second block, or there was a carry in and it is propagated through group 0, group 1 as well as group 2. Okay, so let's look at this diagram again. So that means this C0 would be propagated to C12 only if it is propagated through group 0, group 1 and group 2. Or C12 would be 1 if it is generated in group 2. Or C12 would be 1 if it is generated in group 2 or if it is propagated in group 2 and it is generated from group 1. So this way, this method of carry generation is actually a generic method which could be applicable to any number of times. We can apply it hierarchically. Now let's quickly see what would be the delay. So the delay of this 16-bit adder would be, now there would be a 1 gate delay because of generation. There would be 2 gate delay because of generating P0 and G0. So basically to generate group propagate signals there would be 2 gate delay, and similarly to generate this C4, C8, C12 it would and C16 it would require another 2 gate delay. So 2 plus 2 plus 1, and then finally there would be 2 gate delay to generate this final sum. So the total delay would be 7 gate delays, which is even lesser than the previously we received 11 gate delay. And further, more interesting thing is that even there is a 64 bit adder, the total amount of delay in case of 64 bit adder would be 9 gate delays, which is substantially less than 128 gate delay in case of a ripple carry adder. Okay, or in case of a regular CLA or a blocked level CLA, 64 bit adder will have a delay of the order of 64 gate delays. Okay, so this is how we can generate, we can see how optimally we can create adders, which could be fast, which could be efficient, but of course there is a cost in terms of area. So we have to pay in terms of area, we have to add more and more gates so that we can have an optimized circuit.